What is this? Oh my God, no way you've been. That happened to me. Yes. I'm still. Perfection. That's so. Hey, look at this goal. It is absolute perfection. Look at this.
All right. Hey everyone. The ones who are here at least. So, hey, so I want to finish up talking about graphs, or specifically graph traversals. We will then talk about searching in graphs, but I want to talk a little bit just to review what's going on here and to review the code from last time. And then we'll move on from there. Hopefully, we'll also talk about finding paths in the graphs. So, no quiz today, but there's an exciting lecture. Okay. So what were we trying to do, basically? We're trying to say, okay, let's say that we have a graph, and essentially we want to print out all the elements in the graph. Printing out the thing, well, if you can't do that, you can't really handle anything. But you might also imagine that you're just like walking across the graph and you're trying to find a specific node or something, right? So like, I want to know whether node 5 is somewhere there, and maybe the only way that I can do it is just like walk along the graph until I find the thing that I'm looking for, something like that. Okay. So we were talking about two strategies for traversal, right? So one strategy was breadth first. So the idea here is if I start with node 1, this is arbitrary, right? So I can start with any node. But if I start with node 1, then what I'll do is I'll first look at the neighbors of node 1, meaning the nodes that are connected to it using an edge. So this would be 6 and 3. Yeah.
That's 7, 8, 9. 7, 8, 9. Here's that second individual triangle.
That's right. So you would need to start in kind of in nodes in the two components, but we are talking about this component right now. You're right. That's if it's disconnected, you have to start a traversal in at least 2 different nodes here. Okay. So we start with 1, and then we explore the neighbors of 1. And then we'd explore the neighbors of the neighbors, and then the neighbors of the neighbors of the neighbors, and so on. So this is what's called breadth first. This is as opposed to depth first, where what you're doing is you're trying to explore by trying to get as far away as possible from the starting node, right? So you would say, well, like maybe I'll go to 3, and then from 3, I want to get as far away as possible. So maybe I'll go to 4, and then maybe I'll go to 5. 5 it is actually connected to 1. So it's not about like literally getting as far away as possible, but it's about prioritizing going first to the neighbor of the neighbor of the neighbor of the neighbor of the neighbor, as opposed to the node itself, and then just its neighbors, and then the neighbors of the neighbors, and so on. Does that make sense? Kind of conceptual. So, okay. So then we have the actual algorithm, right? So the algorithm is like this. So we have a data structure, which is either a queue or a stack, but we just call it data structure, DS. And this is the collection of all the nodes that we plan to visit but haven't yet. Okay. And in broad strokes, what we're doing here, we're saying, okay, start with some node and then say, okay, I want to visit that. So this is this part. So this is adding the first node. And then what we do is repeatedly get a node to visit from DS and add all the neighbors of the node that we just visited to DS to the collection of nodes that we want to visit eventually. Right? And we just keep doing that. Yeah.
Why couldn't you just like go through each component of the matrix?
We could, if it's a matrix, then we could. So and in fact, we do keep a list of the names in our specific implementation, so you could do that as well, right? So if you remember, in our implementation, we actually had like all the nodes. One issue, and that will be more apparent hopefully today, if not then on Monday, is that sometimes we want to basically walk along the graph until we find the thing that we're looking for. And in that case, if the graph is very large, then what you want to do is actually like literally walk along as opposed to like list all the possible things because there's too many things to list. Yes. So for now, so the question was, what's the purpose of traversing? And the answer is right now, it's kind of an artificial task, right? So right now it's just like print the nodes in some order. We will have examples of where it's actually useful later on, hopefully today, if not, then on Monday.
A question about the database code.
Yeah.
Do we ever so when we initialize the graph, can we initialize the node names as well? It just looks like it's the empty dictionary.
That's right. It's the empty dictionary because the number of nodes is 0 by default.
But if it wasn't,
if it wasn't, then they are unnamed. Yeah. Okay. So, okay. So, all right. So, sorry. So kind of to repeat the basic idea here, because that's kind of the important thing, right? So visit, then say, add all the neighbors of the node that we just visited to the collection of nodes to be visited, and keep going until we don't have any more nodes that we plan to visit, which means that we're done with at least the component of the graph that's connected. Okay, so let's go back to the implementation. I sent out the code from last time on Piazza just now. If you don't have it, I do hope that you code along. I think kind of this code is like long enough that just looking at the implementation doesn't make sense. I did at the very end have a bug last time. So if you did code along with me, then this should be .head rather than .head next. So it's fixed on Piazza. If it's in your code, it should be like this. Okay. So this is the implementation of what I was just talking about. So I have my DS and I start with whatever is the starting node. And then I keep going while DS is not empty, right? So what I keep doing, I keep visiting nodes and then adding all their neighbors to DS if they haven't been visited yet. Yeah.
Add just on queue.
Well, it's on queue for queue. So if you remember what we did in ds.py, because I wanted to change this to stack eventually as well, I named them add and get for both stack and queue, even though, as you're saying, traditionally in queue, it's called on queue dequeue, and in stack, it's called push and pop. But I wanted to name them the same thing so that they can swap queue and stack. Yeah.
Did you add that code to the Piazza thing?
Yeah, that's from last time, not today, but so this is in the code from whatever Monday. Yeah, it is. Yeah. So Maybe not. So I remember it wasn't pinned. This is graph. Oh, okay, maybe you're right and I didn't. Okay, so I will do that now. Yeah, I think, oh, yeah, I remember now because we wrote it together in class. Yeah, okay. Okay. So, all right. So this is the idea. So what do we do? So we print it if we haven't printed it already. So we keep track of what was visited and what wasn't visited. And that's because it might be that a node is neighbors with two different nodes. So it might be that it was visited before for a different reason, right? So then if it wasn't visited, we visited and we add every unvisited node to the queue. Or rather to DS, right? So how do we do it? We keep all the neighbors as a list, specifically a linked list. So we just go through the linked list, and for everything that's not visited, we say added to DS. Make sense? So, okay. So now what I want to do is expand the example a little bit so that we can see the difference between depth first and breadth first. The issue here is that if you look at just this graph, so here YVR, Vancouver is connected to YYZ, Toronto both ways, and then Toronto is connected to JFK. But if you start, for example, from YVR, then whether you're doing breadth first or depth first, you're going to go to YYZ, and then the only thing that's left to visit is JFK anyway. It won't make a difference whether you're doing breadth first or depth first, right? So let's connect Toronto to Montreal as well. So Montreal is YUL. How many people, what people know this? I don't know if they do. But anyway, so all Canadian airports for like weird historical reasons that have to do with naming radio stations in the beginning of the 20th century start with Y. Yeah, so that's why like this doesn't have like anything that's to do with Toronto, but this is nevertheless Pearson. YVR is named a little bit better. YUL, same as Toronto. Anyway, okay. So if we're doing it like this, and if we start with YVR, then it matters. Then it matters if we also connect it to JFK. Yeah, let's do it maybe like this. Then it matters whether you are doing breadth first or depth first, and that's because if you start, let's say, from YYZ, then you will want to go to JFK's neighbor before you get to YUL and YVR or something like that. So like this. Okay, so to do this, what I want to do is I want to first add the new airports. So I'll add YUL and I'll add LAX and I'll add SFO. And then I'll need to also put in the new edges. So I'll connect YYZ to YUL. And I'll connect JFK to LAX. And I'll connect LAX to SFO. Okay, so let's now run this. No YUL. I did add YUL. What do you mean? Oh, thank you. Okay. So this is what we get. So we started with YVR and we're doing breadth first, right? So if we're doing breadth first, then what we expect is YYZ, because YYZ is the only way to go from YVR. And then we expect the neighbors of YYZ. So that would be YUL and JFK. And then we expect the neighbors of JFK. The only one that's left is LAX. And then we get SFO. Make sense? So breadth first means the starting node and then the neighbors. In this case, the only neighbor. So now essentially YYZ is the starting node. And then we get the neighbors of YYZ. So in some order, JFK and YUL. And then whatever's left. Does that make sense? Yeah.
If there were branches extending, like two branches extending from YUL, then you get those neighbors and go down those branches as well.
Yeah, so in some order, but the point, the point is we do the neighbors first, and then the neighbors of the neighbors, and then the neighbors of the neighbors of the neighbors. Okay, so this is as opposed to depth first search, where we go to the neighbor and then immediately to the neighbor of the neighbor, immediately to the neighbor of the neighbor of the neighbor, while skipping some of the closer neighbors, right? So we're trying to get away from the original node first. Okay, so to remind you, this is how it would go theoretically. So here, if we start with 1, then we're saying, okay, so 6 and 3 are going to be added to the stack. Then we get something from the top of the stack. So we get, for example, the 6. So we would visit 1, 6, right? And now we add 6's neighbors. So that would be 5. So 5 gets added to the stack. And then we immediately go to the neighbor of 6. We immediately go to 5. So we go initially 1, 6, 5, while skipping 3 and 2. Well, 3 really we're skipping for now because it's not at the top of the stack. Whatever is added the latest gets popped the first from the stack. Is that making sense to everyone? Questions? Okay. There's something in Discord. Yes, thank you. Okay. Okay, yeah. Cool. Okay. So let's see how that works out if we change the code here. So all we need in order to change the code is to just change the queue to a stack. That's kind of the beauty of it. So I'll just copy and paste this entire thing. And I'll name it depth first traversal. And I'll just change this to be a stack. Everything else remains the same. So let's try to run this. It works. Okay. So we now again start from YVR. And then YVR only has the one neighbor, so you definitely go to YYZ. You then go to, we got a little bit unlucky here, right? So you then go to YUL, which is a dead end. So you go to the next neighbor, which is JFK, and then you go to LX, and then you go to SFO. But now we know how to make it so that there is a difference. So the expectation here would be that if you add something here, what's a good Canadian airport? Say it? Why? What is that? Okay. So we'll add YXZ over here. And we'll connect it over here. Is that a real thing? Okay. So what we'd expect is that whichever branch you go, you'll go with this branch to the end, as opposed to going like YUL and then JFK. So let's try that. And I didn't actually change this to breadth first. So that might not have been necessary, but should work anyway. So now we go from YVR to YYZ definitely. And then we go JFK, LAX, SFO. And then the thing that's left is YUL, and then we go to YXZ, right? So the depth first is we first go, so YVR, no choice here, and then JFK, LAX, up until the end SFO. So that's the order here. And only then do you get around to YUL, YXZ. Yeah.
Decide which direction.
The question is, how does it decide which direction it goes? And the answer is, what it does is it just goes through the linked list that lists the neighbors of every particular node, and it adds them to DS in that order, right? So that means that the exact printout is going to depend on the order in which I put the edges in, right? So let's actually, does that make sense to everyone, or do people want to like go back to the linked list representation? Because that's a good question, actually. Who wants the linked list representation? Okay, not zero people. Okay, so here's what's going on. So we are adding those nodes, right? So what happens here is we're starting to build up So we are starting to build up our graph. And the way it is this is, node 0, and then node 1, node 2, node 3, node 4, node 5, node 6. And initially, doesn't have any neighbors. So it doesn't have any neighbors means that there is a linked list. It's just that the head is just null. So then we say put edge name. And the way it works is we are saying, okay, there is an edge between YVR and YYZ. And the way we insert is we insert in the beginning of the linked list. So this linked list becomes YYZ goes to null, right? And then we're saying I want YYZ to YVR. Sorry, this is Y. Sorry, so this is actually the second one. So this would be the second one, and we also add YVR here, right? So this is the first two lines. Those are added like this. And then we say put edge name YYZ to JFK. So that means that JFK goes in here because we insert in the beginning of the list, right? And then we say YYZ to YUL. So that would be like this. And then we say JFK LAX. So JFK to LAX. So that goes like this. And then we say YUL to YXZ, which might be made up. So that would be like this. And then we add our LAX to SFO. I missed that. So this is SFO. So this is like this. Okay, so that's our representation of the graph. Yeah.
Second line that we put an edge between YYZ and YVR. Should we write YVR neighbors or YYZ?
Didn't I do that? Oh, yeah. Typo. Thank you. Yeah. YYZ. Yeah. Okay. Thank you. So that's what we have. And then let's look. So let's try to put all of those together. Let's see if I can manage that. Oh, that's not the one. Okay. So this is what we have, right? And then we are doing depth first, right? So here, what we're saying is, okay, YVR, add YYZ to the stack. And then we take YYZ out of the stack and visit it. And we add the neighbors of YYZ to the stack. We know the order of the neighbors because we know in which order we added them. So the stack is going to be YUL, JFK, YVR. Except YVR was already visited, so it wouldn't be added. So what's going to get added to the stack is YUL and then JFK. Okay. And JFK gets added last to the stack. So JFK is going to be the next one visited, which indeed is what happens. So JFK gets taken out of the stack, JFK gets visited, and the neighbors of JFK, which is just LAX, get added to the stack. And then we take LAX out of the stack, LAX gets visited, and the neighbor of LAX, SFO, gets added to the stack. And then SFO gets visited, gets taken out of the stack, has no neighbors, so it just gets visited. And at this point, YUL is still waiting around in the stack, but now it's the only one in the stack. So that gets taken out of the stack, gets visited, and its neighbor YXZ gets added to the stack. And now YXZ is the only thing in the stack, gets visited, has no neighbors, and we're done. So the question initially was like, how do we know whether YUL or JFK gets visited first? And the answer is, well, in our implementation, this has to do with when it was that the edge got added, just in the implementation. Yeah. Yeah. It's not connected to SFO, but when we visited YYZ, we added YUL and JFK to the stack. It's just that JFK got added second, which means that when we were looking for neighbors of YYZ to visit, JFK got visited first. YUL was waiting around in the stack until we were done with JFK and whatever was connected to JFK. Is that cool? Other questions? All right. Okay. So this is kind of like this. So I now want to do something that you might or might not consider redundant. But so one of those, specifically depth first traversal, you can actually do recursively without using a stack. And that's kind of interesting. So this is recursive depth first traversal. Actually looks very easy. So what do we need to do here? All that we need to do is we need to say, mark whatever node that you sent in as visited, and then whatever wasn't visited, just call DFS on it. Okay, so let's think about what's going on here. So let's say that I start with 1. So if I say DFS 1, what's going to happen? Well, 1 is going to get visited, and then whatever is not visited and is a neighbor of 1 gets called with DFS. So let's say we call DFS 3. So 3 gets visited, and then we say, well, we'll call DFS 2 and we'll call DFS 4, but first we'll call, let's say, DFS 2. So 2 gets visited. And then we say, okay, whatever is not visited and is neighbors with 2, call that. So we call DFS 5. So you'll see that this is the same idea with trying to get as far away from the initial node as possible as soon as possible. Right? So we say, DFS, so DFS 1, that called DFS 3. Eventually, it'll call DFS 4 as well, and eventually it'll call DFS 6. But first, we call DFS 2. And then we call DFS 5. Yeah.
But you did at some point go in circle.
So you're right, and there are cycles here. So that's why we actually keep track of which ones were visited. So if something was already visited, we don't call it again. Right, so you're right. So if there is a cycle and we don't keep track of what was visited, then yeah, like we'll keep just like imagine that we just have 1 and 5, then like a DFS 1, DFS 6, DFS 1, DFS 6, DFS 1, DFS 6 forever. Yeah. So that's why we mark things as visited. Okay. Does this make sense conceptually? Okay, so let's implement it. So we'll call it like DFS recursive. And it'll take current, which is the first one. And it'll take the visited array, which we need to initialize first. So if I don't want to be kind of annoying about it, I can make it so that visited is initially something that's not that I need to initialize or something. So I can say that by default, it's like none. And then I'll say, okay, so if visited, so in Python, I don't know if we ever did is none. So is means that the IDs are the same. I can also say equals equals, which is what we've done before. So is means like, is the ID of this object the same as the ID of the right-hand side? For none, it's the same because there's only one none object. So we initialize visited in the same way. Know what that says. So now what we're going to say is, okay, so we have our visited thing and we initialized it if we didn't want to initialize it. And now we'll say, okay, so for the neighbors, so I'll say her current neighbor is. You'll notice that Copilot is struggling a little bit here. I need to correct it and stuff. Hopefully I correct it correctly. So I will just go through all the neighbors of Kerr. And I'll visit them. So, okay. Visited Kerr. Print Kerr. So this is actually G. Node names Kerr. So if you remember, node names is our list of all the indices, right? And now what I'll do is so this is G. So let me just quickly say, so cur I is node names cur. And now this is going to be nodes cur I. And this is going to be visited cur I. And I print cur. So now I'll just go and add and call DFS on all the neighbors that have not been visited yet. And I'll call, sorry, so I gave up on typing, but I'll call DFS recursive like so. Okay, so there is like a little bit of an annoyance here because I want to call it with the name. But I need the index in order to access the neighbors, right? So here, like in order to get the index, I need like node names reverse. This is why. Does that make sense? Yeah.
The node names, but in reverse, that's a dictionary.
So node names reverse is I give the name, I get the index. Node name is I give the index, I get the name.
Okay.
So it's kind of like node names. Wait, did I mess it up? Sorry. So node name. So here. So yeah. So node name. Yes. Sorry. So node names actually get node names gets the name, and then node names reverse is index to names. So actually, we need node names. Apologize for that. Okay, so it's like node names YYZ is 0, and node name reverse 0 is YYZ. All right. So, okay. So, the point here is not this implementation, which is slightly annoying with trying to go between the indices and the names. The point is to just demonstrate that the stack, which I promised I think in the beginning of the course to explain why it's called the stack and the heap, and this is the point where I explain it. The point is that basically calling functions recursively is equivalent to maintaining a stack. So think about it like this. We have this graph, and we call DFS on YVR. So what happens then? DFS of YVR calls DFS YYZ. DFS YYZ is it needs to call DFS JFK and also eventually DFS YUL, right? So first, what's going to happen is it's going to call DFS JFK. And then DFS GFK is going to call DFS LAX. And this is going to call DFS SFO. Okay. But once this is done and we return here and we return here and we return here, this is also going to call DFS YUL, and this is going to call DFS YXZ. So of course, all I've done here is just reproduce like the part of the graph that's along the lines that I'm exploring. Yeah. There, I typed one of them wrong. So okay. So this is of course just so if you just look at it like as a picture, this is basically the same as this graph, except some of the arrows are missing because we don't go back. If we already visited YVR, we don't go back to YVR, right? But the way it works is this calls this, calls this, calls this, calls this, and this waits around until you get to call this, right? So this works like a stack in the sense that you call JFK and then you call LAX and so on. And the first thing that gets called is the first thing that gets printed. But eventually, once this stack is empty, you'll call DFSREC YUL. Right? So this is why I didn't need an explicit stack there, which is what I needed for that first search without recursion. I can just use the built-in function calling mechanism in order to achieve the same thing. And this, I think I did kind of call it that in 180 as well, but this picture is called the call stack, right? So it's called the call stack precisely because the first thing that gets called, it executes right away, and then this executes right away, and then this executes right away. And then eventually, once this branch is over, you'll make those calls. Does that make sense? So when you're looking in the C debugger, which broke 2 weeks ago at ECF, unfortunately, but on your laptop when you're using the debugger for project 2, so what you see is that the variables that are the local variables are stored in what's called the stack. And that's because so in memory, what happens is all the local variables here are stored, and then also all the local variables here are stored, and then also all the local variables here are stored, and they're stored on what is called the call stack. There is a deeper reason for this, which you'll see in second year, which is that not just the local variables, but the parameters are stored like this. So there's multiple copies of the parameters. So for example, of the parameter cur that is stored, and they're all stored kind of in a stack on literally kind of on top of each other, right? So there is like the cur that's stored here, and the cur that's stored here, the cur that's stored here, and so on. You'll really hear more about it in second year. This is more like about fulfilling the promise of telling you why it's called the stack. Okay. The questions about why, kind of how this works, or rather like how DFSREC works, not the call stack stuff. Okay. So this is kind of cool. And with the queue, there is not an easy way to implement this with recursion, but I think it's kind of remarkable that kind of conceptually you can just, because this stack structure is built into the function calling mechanism, you can just do this without explicitly using a stack, and it's just 3 lines and it works. Yeah. Sure. Is it broken? It's like quite likely. Okay. Key error 0 per neighbor data. So this is node names. So this is G node names. Per neighbor. Oh, okay. So we need like this needs like the G names thing. Wait, I don't need the names. Like this is just per neighbor data. So this is it's like about the indices. Node names cur also don't need it. No, this one I do need. So cur, we call it with 0. Why we are. So here we say DFS rec. Okay, so here we need the names. Why we are. Node names, cur, neighbor, data, key error. Okay. Progress. So now, sorry, so I got a little bit confused with my node names and node names reverse. And now we evidently got into an infinite recursion situation because we called something, because we are calling something that's been visited. So just say, if this has been visited, then we just return. Out of time. I'll fix it and let you know on Monday. Thank you. All right, I'll see you. Bye. Yeah, sorry. So I like really wanted to keep both the indices and the names, and it was kind of improvising here. Yeah. Uh-huh.